Section: Introduction. In this section, we explore the advancements in large language models, LLMs, and large multimodal models, LMMs, across various domains like language, images, videos, and 3D point clouds. We note that recent efforts have focused on enhancing these models with chain-of-thought (CoT) reasoning, which has improved their performance in areas such as mathematics, science, and coding. However, we find that the application of multi-step reasoning in image generation is still underexplored. We observe that autoregressive image generation shares similarities with LLMs and LMMs, as both convert target data into discrete tokens and predict content based on previously generated tokens. LMMs utilize CoT to simplify complex problems, which allows for better computation and alignment with reward models. We question whether we can apply similar verification and reinforcement techniques to image generation. To investigate this, we use ShowO, a new discrete generative model, as our baseline and evaluate it on the GenEval benchmark for text-to-image generation. We focus on two main areas: using outcome process reward models, ORM, PRM, as verifiers and optimizing preference alignment through direct preference optimization, DPO. We first compare ORM and PRM as test time verifiers. We find that while ORM significantly improves results, PRM offers limited benefits. Next, we explore the balance between inference time and post-training performance, using DPO to enhance the model's reasoning capabilities. Our findings show that DPO with iterative training yields better results than the fine-tuned ORM. After examining these techniques individually, we combine them to leverage their strengths in autoregressive image generation. We propose 3 integration methods, all of which lead to improved outcomes, highlighting their complementary nature. Our experiments reveal the potential of applying CoT reasoning to image generation and identify areas for enhancing reward models. We introduce the Potential Assessment Reward Model, PARM, which evaluates the generation process step by step, addressing the limitations of ORM and PRM. PARM adapts its assessments based on the clarity of images at different stages and selects the best final output. We also present PARM++, an enhanced version that includes a reflection mechanism for self-correction. This model checks if generated images align with the input text and prompts adjustments if discrepancies are found. Our results show that PARM outperforms both ORM and PRM, improving the baseline model by 24% on GenEval, while PARM++ further enhances performance by 4%. In summary, we provide a comprehensive study on applying CoT reasoning to autoregressive image generation, highlighting the effectiveness of our new reward models, PARM and PARM++, which significantly improve text-to-image generation quality. Section Summary. In this section, we explore the application of chain-of-thought reasoning strategies to autoregressive image generation, demonstrating their potential to enhance performance through systematic investigations of test time verification and preference alignment. We introduce 2 novel reward models, PARM and PARM++, which improve the quality of text-to-image generation by adaptively assessing the generation process and enabling self-correction, achieving significant performance gains on the GenEval benchmark. Section: Our investigation. In this section, we investigate chain-of-thought (CoT) reasoning, which has been effectively used to tackle complex problems in language and multimodal understanding. Our goal is to see if we can verify and strengthen image generation step by step. We focus on the autoregressive image generation task, as seen in models like MaskGit and LlamaGen. This task uses a data representation similar to that of large language models, LLMs, and large multimodal models, LMMs, achieving performance comparable to continuous diffusion models. It works by converting images into discrete tokens through quantized autoencoders, allowing us to apply a specific loss function during post-training. The model predicts 1 or more tokens at each step based on previous outputs, creating reasoning paths that can be verified step by step using reward models. For our experiments, we choose ShowO as our baseline model, which is a cutting-edge autoregressive image generation model. We evaluate its text-to-image generation performance using a rigorous benchmark called Gen-Eval. This benchmark requires the model to produce images that are not only visually appealing and aligned with the text but also accurately represent object attributes and their co-occurrences. We explore 3 strategies to enhance the step-by-step decoding of image generation: test time verification, preference alignment, and a combination of both. We compare 2 types of test time verifiers: the outcome reward model, ORM, and the process reward model, PRM. We implement and assess these models in the context of autoregressive image generation. For ORM, we evaluate the generated image at the final step using a best-of-n strategy based on multiple reasoning outputs. Initially, we use a zero-shot ORM with a pre-trained model called LLAVA1 Vision, which helps us assess image quality by providing binary responses of yes or no. We then curate a dataset of 288,000 text-to-image ranking examples to fine-tune the ORM. This involves generating diverse text prompts and synthesizing images, which we label based on their quality. For the fine-tuned ORM, we enhance LLAVA1 Vision's ability to evaluate image quality and text alignment using the curated dataset. We train the model for one epoch with a specific batch size and learning rate, allowing it to better understand object composition and visual text relationships. In contrast, PRM provides a reward score for each candidate at various steps during the generation process. We also start with a zero-shot PRM using LLAVA1 Vision and curate a dataset of 10,000 stepwise text-to-image rankings for fine-tuning. Detailed implementation information for PRM can be found in the appendix. Section Summary. In this section, we systematically investigate the application of chain-of-thought reasoning in autoregressive image generation, focusing on models like SHO-O and employing test-time verification strategies such as Outcome Reward Model, ORM, and Process Reward Model, PRM, to enhance image quality and alignment. We curate extensive datasets for fine-tuning these models, aiming to improve step-by-step verification and overall performance in generating high-quality images. Section: Experiments and Insights. In this section, we compare the test time verification results of ORM and PRM using a best-of-20 strategy, as shown in the middle of the table. Our findings indicate that test time verification can significantly enhance generation performance. Specifically, the fine-tuned ORM serves as a test time verifier, achieving a notable improvement of 10 percentage points over the baseline score of 53% on Gen-Eval. This suggests that current autoregressive image generation models, like LLMs and LMMs, struggle with inconsistent decoding paths, making test time verification crucial for identifying the most reliable reasoning path. We also observe that ORM provides stronger enhancements compared to PRM. While ORM shows a clear advantage, PRM only offers marginal improvements, such as a 2 percentage point increase on Gen-Eval after fine-tuning. This difference stems from 2 main factors. First, early images are often too blurry for PRM to effectively analyze their visual features in alignment with text. Second, later images show minimal differences, making it hard for PRM to distinguish between them. In contrast, ORM evaluates images at the final step, where there is enough visual and semantic information for accurate assessment. Furthermore, fine-tuning with ranking data improves verification results and demonstrates better scaling performance. As illustrated in the figure, both fine-tuned ORM and PRM outperform their zero-shot versions, achieving higher scores with larger sample sizes in the best-of-n selection. Additionally, as the sample size increases, fine-tuned reward models show more significant improvements, indicating a better scaling response to test time computation. This underscores the effectiveness of our curated ranking dataset in enhancing reward accuracy and scalability across a wider range of candidates. To avoid reinforcement learning, we utilize DPO, which employs an implicit rewarding mechanism by training on a ranking dataset of paired preferred and dispreferred responses, corresponding to well-generated and poor-quality images. We have already created a substantial amount of ranking data for training ORM, labeled with yes and no to indicate generation quality. Using the 13,000 unique text prompts from the ORM training dataset, we randomly pair two generated images for each prompt, one labeled yes and the other no, resulting in 10,000 paired data points for DPO alignment. Since autoregressive image generation models are trained with cross-entropy loss, we can directly apply the maximum likelihood objective in DPO to our context. The parameterized policy is initialized from show-o and optimized during training, while the reference policy is also initialized from show-o but remains unchanged. The objective encourages the model to assign a higher likelihood to preferred images over dispreferred ones, aligning with our curated preference structure. We conduct training over one epoch with a batch size of 10 and a learning rate of 0.00001. After the initial DPO alignment, the model generates images that better match preferred responses. Inspired by iterative DPO, we refine this alignment by using the newly aligned model to create updated ranking data based on the text prompts. We label these new images with yes or no, using the same method as before. For each prompt, we collect paired images labeled yes and no, excluding samples where all images receive the same label, resulting in a refined DPO ranking dataset of 7,000 samples. By conducting another round of DPO, we can further improve the model by learning from more informative preference relations, iterating the DPO training process once with the same configurations. Finally, we present the evaluation results of DPO alignment at the bottom of the table, comparing it with test time verification performance. Our observations reveal that DPO alignment effectively enhances generation performance. The initial DPO alignment improves the baseline model's performance by 9 percentage points on Gen Eval. With iterative training, these gains extend to 11 percentage points, demonstrating the effectiveness of a refined preference dataset in strengthening model alignment with desired outputs. Notably, initial DPO matches the performance of test time verification, while iterative DPO surpasses it. After the initial alignment, the model achieves performance comparable to the fine-tuned ORM, the best variant for verification. However, with iterative alignment on refined ranking data, the model outperforms all test time verifiers by 2 percentage points over the fine-tuned ORM, highlighting the potential of iterative DPO to progressively enhance image generation capabilities through updated ranking data. Section Summary. In this section, we demonstrate that test time verification significantly enhances image generation performance, with our fine-tuned ORM model achieving a notable plus 10% improvement over the baseline. Additionally, we show that DPO alignment, particularly with iterative training on refined ranking data, not only matches but ultimately surpasses the performance of test time verification methods, indicating its effectiveness in improving autoregressive generation models. Section: DPO alignment plus test time verifiers. In this section, we explore how to combine test time verification and DPO alignment, building on our previous findings that each technique is effective on its own. We investigate 3 methods to integrate these approaches for better image generation, utilizing the flexibility of verifiers and the reinforcement provided by DPO. First, we consider DPO with guidance from a reward model. We recognize that DPO can face challenges with responses that fall outside the expected distribution. To address this, we suggest using prompt-only datasets during post-training and employing a reward model for real-time preference guidance. We utilize our fine-tuned online reward model, ORM, to give broader preference feedback while keeping the original DPO loss intact, using the same training data and setup as in the initial DPO alignment. Next, we look at verification after DPO alignment. We find that verification and DPO can complement each other effectively. They function independently at different stages, post-training and test time. DPO enhances the model's internal knowledge distribution for better reasoning, while verification helps select the best reasoning path from this refined distribution. Thus, we apply the fine-tuned ORM for selecting the best option directly after DPO alignment. We then combine the strengths of DPO with reward model guidance and test time verification. Our aim is to achieve optimal alignment, improving the model's ability to generalize during training and ensuring reliable image generation during inference. From our research, we see that reward models are useful for selecting decoding paths and providing preference guidance. However, we also identify areas for improvement. The ORM excels at choosing the best final outputs but does not evaluate each generation step in detail. On the other hand, the preference reward model, PRM, is effective for tasks like mathematics but struggles with early-stage images in autoregressive image generation, as they can be too blurry for reliable assessment. To address these limitations, we propose the Potential Assessment Reward Model, PARM, designed specifically for autoregressive image generation. PARM operates in a stepwise manner, using a potential assessment mechanism to tackle the evaluation challenges faced by PRM. It also performs a selection process among high-potential reasoning paths, benefiting from ORM's strengths. PARM consists of three main tasks. 1. Clarity judgment. We sample multiple reasoning paths for image generation and evaluate each partially generated image for visual clarity. If an image is deemed unclear, we skip to the next step. This prevents scoring early, blurry images and ensures we only consider clear steps for rewards. 2. Potential assessment. For each clear step, we assess its potential to lead to a high-quality final image. If a step is not promising, we truncate that path. If it shows potential, we keep it for final image production. This helps us identify the most promising intermediate steps and eliminate low-potential options. 3. Best of N selection. After the previous tasks, we select the best candidates from the remaining high-potential paths. If no paths are left, we choose the one with the lowest chance of being labeled as unclear. This final selection leverages ORM's capabilities to ensure a high-quality generated image. To support PARM, we have created a new ranking dataset with 400,000 instances by re-annotating 13,000 text prompts from ORM ranking data. This dataset is divided into three subsets for the evaluation tasks, containing 120,000, 80,000, and 200,000 instances, respectively. Further details on the data formats can be found in the appendix. Section Summary. In this section, we explore the integration of test time verification and DPO alignment to enhance image generation, proposing the Potential Assessment Reward Model, PARM, that evaluates clarity and potential at each generation step. We also curate a new ranking dataset to support PARM's capabilities, aiming to improve the model's generalization and output quality during inference. Section: Experiments and Insights. In this section, we revisit our earlier work by applying PARM to various methods that enhance autoregressive image generation. Our findings indicate that PARM is the top-performing reward model across different strategies. We see that PARM serves effectively as a test time verifier, outperforming other reward models by a significant margin, such as a 6% improvement over the fine-tuned ORM. Additionally, PARM scales well with larger test time computations, suggesting it can improve further with increased resources. We also find that PARM surpasses the iterative DPO method, which is an improved preference alignment strategy using refined data. Moreover, PARM effectively utilizes complementary strengths during post-training, consistently achieving higher integration scores than the fine-tuned ORM. These results highlight PARM's versatility and robustness as a reward model for autoregressive image generation. With PARM, we enhance our baseline model, SHOW-O, leading to superior generation performance. Our best configuration, which combines PARM with iterative DPO during both post-training and test time, achieves a score of 77%, improving the baseline by 24% and exceeding the Advanced Stable Diffusion 3 by 15%. We observe significant improvements in areas like object placement, color accuracy, and attribute binding, showcasing our model's strength in complex compositional tasks. We present numerous qualitative examples that illustrate our findings. We notice that the baseline model often struggles with accurate spatial relationships and object attributes. In contrast, our approach effectively addresses these issues, maintaining the integrity of spatial relations and overall fidelity to the text prompt. Next, we introduce PARM++, which enhances PARM by incorporating a reflection mechanism to improve text-to-image quality. This reflection strategy, recently applied in large language models, allows for self-correction. Unlike language models that can freely generate and refine text, image generation models depend on descriptive text prompts and produce images as output. Therefore, the reflection process must be managed by an external reward model that identifies misalignments and offers explanations. The image generation model also needs fine-tuning to understand and respond to these reflections for effective self-correction. In PARM++, after selecting the best output from a set of image candidates, we conduct a reflection evaluation to check how well the final image aligns with the input text prompt. If the image meets the criteria, we confirm it as the final result. If not, we provide a detailed analysis of the discrepancies and the reasons for misalignment. We then input 3 elements into the image generation model for self-correction: the original text prompt, the previously generated suboptimal image, and the identified misalignment reasons. This iterative process continues until we achieve a satisfactory alignment, enhancing both visual quality and image-text correspondence, with a maximum of 3 reflection iterations. To support PARM++, we curate an additional 120,000 instances for the reflection evaluation task, building on the existing 400,000 dataset, resulting in a total of 520,000 data points. For negative data, we select low-quality images labeled as No from the ORM ranking dataset and use GPT-4o to provide concise annotations on the discrepancies. For positive data, we use high-quality images labeled as Yes. The dataset maintains an approximate ratio of 80% negative to 20% positive instances. Finally, we fine-tune Show-O, our baseline model, to enable it to self-correct low-quality images based on textual instructions. Show-O can take both text and images as inputs, allowing for refinement guided by textual feedback. We create a training dataset of 10,000 instance groups from the PARM++ ranking dataset, each containing a text prompt, a low-quality image, a high-quality image, and annotated reflection reasons. This dataset is used to fine-tune Show-O, progressively enhancing the quality and alignment of the generated images. Section Summary. In this section, we demonstrate that our new reward model, PARM, significantly enhances autoregressive image generation, outperforming previous models and achieving a 24% improvement over the baseline. We also introduce PARM++, which incorporates a reflection mechanism for self-correction, further refining image quality and alignment with text prompts through an iterative evaluation process. Section: Experiments and Insights. In this section, we present the results of reflection and self-correction using PARM++. We do not include any DPO alignment during Show-O to avoid conflicts with self-correction fine-tuning. Our findings are summarized as follows. The reflection mechanism in PARM++ greatly improves image quality. When we do not apply reflection, indicated by a dash in the table, PARM++ performs slightly worse than PARM due to the specific training data for reflection. However, when we enable the reflection mechanism, marked with a checkmark in the table, the overall score on Gen Eval increases significantly by 10%, highlighting the effectiveness of this strategy. We also show a comparison of images before and after the self-correction process. The self-corrected images, guided by the reflection evaluation, successfully fix issues like unrealistic elements, incorrect numbers, wrong colors, and poor object arrangements. While the self-correction fine-tuning has a slight negative effect on the baseline model's performance, resulting in a 2% drop in accuracy on Gen Eval, we believe that the reflection mechanism ultimately enhances performance. This drop occurs because training for new features can affect the model's existing knowledge. We expect that future advancements in larger models will help overcome this limitation, allowing them to better manage multimodal information.